faster nanochannels for efficient ionic separation.
Okay, thank you, Chair Tongxin, Professor Tongxin. Okay, and the all greetings. Thank you for the warm invitation from Professor Hall. And I know today's main topic is microproton removal, but I raise this introductions as ionic separation is okay. And further, my major is chemical engineering. So today I bring a topic about the ionic separation, whose name is promotion of monovalent ion transport enabled by fast nanochannels for efficient electrodialysis. And I'm Yuqing Lin. For now, I'm duly appointed by two affiliations, which is Kobe University and ACOST. Okay, membrane technologies attract attentions. Yes, because of its low energy consumptions, reduced investment costs, and high operational efficiencies. Okay, we can see that from this, according to the data from the US DOE report, we can see that the membrane technology separation would use 90% less energies than the conventional technologies, such as distillations, and especially for the separations with high precisions in the fields from the microproton to removal to desalination, and among which the electrodialysis membranes has been widely used in auto treatment processes. Yeah. Okay, these membranes wherein the cation exchange membranes or the anion exchange membranes can selectively let the cations or anions passing through the pore channels to realize the separation under the electron-driven fields. Okay, and specifically for the selective electrodialysis membranes, it can be used for the separate of monovalent and multivalent ions, something like this. Yeah. So today, this technology has been widely used. For example, the electrodialysis or the reverse electrodialysis has been used in resources extractions, redox flow batteries, and fuel cells. It's a good work, but every coin has two sides. Because we're talking about the membranes, so of course the electrodialysis membranes has some limits, which is a trade-off limits. For example, here it confronts the limits from the selectivities and conductivities, and of course its sustainabilities. For example, if we increase its IEC, ion exchange capacities, according to its figures, we can see that selectivity can increase. Meanwhile, its conductivity can also be increased. However, its stability will be compromised. And another thing is, for example, if we decrease the thickness, yes, its conductivity will be increased. However, the selectivity and the stability will also be decreased. So we were thinking how to make a very good membranes for the very efficient air separations. And so we think we'll find our way out is we can construct some pore channels into membranes. And yes, so we conduct a series of works and to make the membranes highly efficient for ion separations. Okay. And this is our first work. It's about we're talking about pore channels. So this work we use the layer by layer work. The method to fabricate membranes is to use the polyelectronics PI and PSS, and they can combine by the electrostatic interactions. And after which we make the glutaldehyde to make a cross-linking surface and to make the surface layer denser. And after which, and we can see this is, we can make some denser structures for the ion separations. And we make it, for example, here we can see that the after the GA coatings, we can see that the membrane thickness nearly remained without big difference. So we can say that if the membrane selectivity increased, we can say that maybe perhaps this is not because of its thickness increased, but just because of its the surface selective layer. Yes, because its after surface cross-linking, so we can see that its process decreased, yeah, from about 3.6 to 3 angstrom. Yeah. And after that, we can say that the divalent ions, yeah, under the certain current densities, the divalent ions, the flux decreased. Meanwhile, the monovalent ion increased. So which results in better selectivities between the monovalent and the divalent ions. So I think after the GA coatings, the membranes, yes, we successfully fabricated. And we were thinking, why what happened? Because it's the if just because its process decreased, and what happened for this kind of two types of ions? And we were thinking maybe because of its the outer surface hydration layers. For example, we make a MD simulation work to modeling the pore channels. And we can say that for the monovalent ions, for example, the potassium ions, the hydration states nearly remained with and without the GA layers. But for the magnesium ions, it's different because its outer surface hydration layers decreased. Yeah, obviously. So we can say that for these pore channels, when we get inside it, the divalent ions will suffer higher energies to strip its outer hydration layers, so it will overcome higher energy to permeate through it. And it's the stable hindrance to prevent its permeate through. And so we are talking about the stable hindrance, these pore channels. And after that, we were thinking, yes, the pore channels decreased, but the resistance increased. So it's not so good work for us to make a highly efficient membranes. So we are thinking if we're embedding some highly porous structures inside it, and we can just enhance its downline repulsions. And meanwhile, we can remain its highly porous structures. And I think it's good for the monovalent ion permeate. And so we tried, we synthesized this kind of dendrimers, and it's highly branched with the outer surface of the ammonia groups, highly positively charged. And inside it, we think this the internal porous will be increased. So the ions can permeate passing through the freely, but meanwhile, the multivalent ions will be repelled because of its highly positively charged. And we can find that after we embedding this dendrimers, its surface structures nearly remained. And however, for the performances, we can see that this divalent ions, yes, it's log, it's a log axis. So we can see that its divalent ions, its permeate decreased, yes, obviously. But meanwhile, its monovalent ions flux increased, so which results in the highly porous which results in very highly efficient the mono to divalent selectivity, ion selectivity. And this selectivity, I think it's good compared to the state of the art references. And then we make calculations of the resistance. We can see that for the monovalent ions, the monovalent ion potassium ions, its resistance decreased, which means its conductivity increased. So this demonstrates our assumption that after we embedding these dendrimers inside it, the monovalent ions can freely pass through it by overcoming a bit energy balance. But meanwhile, which is contradictory for the divalent ions, it have to overcome a higher energy balance. And because of its energies, these interactions, we can say that the ammonium groups against the monovalent ions is only about 15, but for the multivalent ions, it's doubled. So first work, we just use the Dirac repulsions to realize the monovalent and divalent ion separations. And we are thinking, is it possible to have the third way to realize the monovalent and divalent ion separations? And so we are thinking maybe yes, and so we are thinking maybe the hydrogen bondings itself is a kind of a kind of method to realize it. We can say that because we can say that if we're introducing some high polarity groups inside pore channels, this is ionic cross-linking. So this membrane pore channels is constructed by using the acid and alkali pairs. Yes, electron interactions. But if we introduce more highly porous, highly hydrophilic functional groups inside it, and perhaps these groups with high polarity will grab the water molecules. And because water molecules is a coat of the ions, so perhaps when we grab their coats and the ions will be retarded, and then the separation can be achieved. And so we make some demonstrations, okay? And we can see that by tuning the pH values, we can see that they're selectively increased because of this positively charged. Yes, it's okay. And however, we actually also find that if we by changing the polarity of the membranes, yes, the graph, the auto graph capability increased. We can see that when the membrane is in protonated states or deprotonated states, it has more hydrophilic capability than its regular states. So which means we can demonstrate in QCMD analysis that in the protonated or deprotonated states, it can absorb higher water molecules. Yeah. So and under such circumstances, we can see that if the membrane can absorb the higher water molecules, so it can higher hydration capability to absorb this hydration, this ions, and so this ions may also be captured by this pore size, the pore interaction itself, so it can be retarded. And so, based on the assumptions, we also calculated the interaction energies between the ions and the pore channels. And yes, it exhibits a positive correlation to our assumptions. So I was thinking, yes, if the membrane is highly hydrophilic, it has some positive effects to absorb the multivalent ions with the stronger hydration energies. And yes. Okay, and so this is our synchronous versatile interactions. And so we also make some simulation works about this this kind of this phenomenon. We can say that with the higher hydration, this assumptions, we can say about the two-dimensional distributions. We can say that for this monovalent ions, it's still nearly the same when passing through the pore channels. But for the divalent ions, yes, we can see that it decreased a lot. So which means its distributions become lower and lower, fewer and fewer. And according to dynamic, the RDF, we can say that if it can passing through the pore channels, it will undergo a more severe dehydration phenomenon because it have to overcome the larger the energy barriers to overcome. Okay. And for the final work, what we're thinking, it's because we're just talking about this downline exclusions, the stereo hindrance and hydration, and so we're thinking if we can use all of which this together, can we just make some works to separate the monovalent ions freely, notwithstanding their ionic chargements? So we try to make some PIM works here. And this PIM works, we because it's intrinsic porosity, so its pore channels can very tight to let the monovalent ions freely charged. And we think this, if we make some functionalizations, this membrane can simultaneously realize separate the protons and hydrogen ions, which means it can be used for the acid and alkali recoveries at the same time. Okay, after the surface quantizations, we can say that there's very few differences. Because its porosity is nearly the same, its pore size is nearly the same, its surface microstructure is nearly the same. So the only change is its surface chargements, which means its pore size is the same. It become to be a bit positively charged. And we're using this characteristics and this kind of membranes if we can use it for this electrolysis process. If we make this membrane very intact to tune its pore size, its no defect, we can say that this membrane can be used for the alkali recovery because this membrane's pore size is very tight, so it can separate ions with larger sizes. And on the contrary, as membranes, because it's highly positively charged, and so these membranes, if we use it in the diffusion dialysis, and these membranes can use for the acid recoveries, because the material ions can be rejected by its Dolan exclusions characteristics. So, which means these membranes can be realized for the acid and alkali recoveries to separate the comprehensive monovalent ions. Because we use both the pore channels and the pore sizes and pore properties. Yeah. Okay, and here's my closing remarks. The channel architecture in other films can directly influence separation selectivity. And the first chapter 1 and chapter 2, interior electrostatic exclusion can be best expressed in Armstrong confinement channels by embedding the dendrimers. And the third one is the versatile interaction with the monovalent and the material ions can be tuned in ionic cross-linking networks. And then we think, as such, the ionized Armstrong scale channels can be constructed for simultaneously the comprehensive monovalent ion separation. Okay, and we thank the grants for supporting me for that all this works. And for now, my work at Kobe University is just starting up this stage. So most of my work has been accomplished in ECOST. So please thank the folks and the students from ECOST. Thank you.
Okay, thank you. So next presenter is Professor